Okay, hello and welcome back. In this video, we'll cover section 2.4. We'll take a look at what's called the library of functions, and then also piecewise defined functions. And we'll describe what those are. The library of functions, I've also been given the phrase parent functions. These are a lot of the functions that you're probably familiar with, and it's like the simplest possible version of um, many of the different sort of classic function behaviors. And in our next section, we'll learn how to transform those functions and move them around, shift them, reflect them to create all kinds of possible functions. But we'll start off by looking at these are almost like the function archetypes, the main cast of characters. So let's jump right in. So this is going to be looking at the graphs of the library functions, but also let's do a little bit of functional analysis as well. So I'll just set the rules here. So I'll say for each function, let's produce a graph. So we'll do a quick sketch. Doesn't have to be perfect. And I'll put a couple points on there, usually like 2 to 3 points. We will state the domain as well as the range. We'll decide if the function is even or odd or neither. We'll list any intercepts. We'll think about intervals of increasing or decreasing or constant behavior. We'll locate any local minima or maxima, as well as any absolute minima or maxima. So it's some pretty standard functional analysis. We're going to list some attributes, kind of getting to know each of these. And you've probably seen a lot of these before. So um, the part of why this is useful, and I think why we're going through this again in pre-calculus, is because eventually later on in calculus you look at some pretty complicated functions, functions that are compositions of other functions. It's like you put a bunch of functions together and create some more complicated version. But if we can decompose it and see what it's made of in our mind and how it's maybe a combination of some of these, what I'm calling parent functions, and we know the attributes of each of these sort of separate functions, we can get an idea of what a more complex function would behave like, what its attributes would be. So it's good to know these. I mentioned that they're kind of like the archetypes of um, more complex functions that can be built out of these. And of course, there'll be some in this list that, or there's some that aren't covered. Like for instance, we won't look at the trigonometric functions quite yet, or the exponential or logarithmic functions. We have a pretty good group already. So let's just jump in. The first one is the constant function. We have f of x equals b, where b is a real number. I'm going to call it c. I'm used to representing a constant using the value c, but it's just a label here. So it means that no matter what the input is, the output is always this value c. So we can visualize it, although c could be anything. Let's just say c is some positive integer. So our function in this case would just be a horizontal line. It's constant. It will never change. It's always the same value, regardless of what the input is. Sometimes that's useful. So the domain, well, you look at where the graph exists along the x-axis, and it goes forever in both directions. So it's from negative infinity to positive infinity. The range will just be whatever this value c is. So we can just list a set containing a single value, because it will always be one value. That's why it's part of why it's called constant. It will never change. Um, is it even or odd? Well, we can see it has symmetry about the y-axis. Another way to think about it is if we did f of negative x, well, the input doesn't really matter, so we can say f of negative x equals f of x. It'll always be the same value. So that qualifies as even symmetry. Now intercepts, this will depend on what c is. If c was equal to 0, you would have some intercepts. You would have you would have an x-intercept at every value if c was equal to 0. In this case, we could say we have a y-intercept, and this will be true regardless of what c is. We have sorry, my pen's being a little weird. Let me try to reset this. So we have a y-intercept at the point 0, comma c. So that will be true regardless of what c is. We'll just locate it as c. And if c was equal to 0, well then every point would also be an x-intercept. So it depends on what c is, but for sure we'll have a y-intercept at 0c. And this function is constant over its whole domain. It's always constant. So we can say constant on negative infinity to positive infinity. So constant on the whole domain. Now, minima and maxima. Well, we can say it's kind of both at the same time. Um, any point we could call the minima or maxima. So this one's a little bit vague since it's always the same point. So it'll apply more to some of our other functions. So that's the constant function. Our f of x is just equal to some constant value. So how about the identity function? You may recognize this as a line with a slope of 1 and a y-intercept of 0. Let's create a little sketch. So I usually put points around -1, 0, and +1. That usually helps us locate and anchor our graphs, whatever it is that we're looking for. So we know we should have a point at the origin, a point at 1, 1, and -1, -1. So we get a nice line. It's called the identity function because the input is equal to the output for any point. 1, 1, or we'd have the point 3, 3, and so on. So let's label our points. Here at the origin, -1, -1, and 1, 0. Having these points for each function is helpful because when we start doing transformations, it's helpful to follow where these points go. Do they get rotated, flipped around, stretched out, expanded? So it's a good starting point. So let's list out our attributes. Our domain, is from negative infinity to positive infinity. We can plug anything in here. And the range also, starting from the bottom, negative infinity up to positive infinity. Any output is possible. It has odd symmetry. You can imagine f of negative x would equal negative x, which is negative f of x. So it has that property. You can see it's symmetric about the origin. So we have an odd function. Notice it's also to the first power, an odd power. It has an x and y intercept at the origin. So 2 for 1. It is increasing on its whole domain. And never decreasing. And we can't pick out any, so no local minima or maxima. Also no absolute minima, maximum. Any point that we choose, there will always be a point higher and lower than it. So we can't state any minimum or maximum. This one should be familiar. You've probably done a lot of work looking at different kinds of lines, and so how this one line can be shifted around, flipped around, and all of that. Another one, probably seen a lot, the square function. So this is like the most basic quadratic, a parabola. So let's stick a few points. So it's a parabola, its vertex is at the origin, and we would have the point 1, comma 1, and also negative 1, positive 1. So we get our nice parabolic shape, upward U shape. So I'll label 0, 0, 1, 1, also negative 1, positive 1. 3 points of interest. All right, the domain. This will also be negative infinity to positive infinity. And that'll be true for any polynomial. You can plug in any real number and get a real value output. And how about the range? Well, the graph doesn't begin until 0 and then goes off to positive infinity. And we will include 0. Yeah, we're taking a number and then squaring it, so there's no output that should be negative. We can't possibly produce a negative output with a real number input. If we were to plug in I squared would give us a negative 1, but we're sticking to real numbers at this point. Even, odd, well, it's symmetric about the y-axis, and we can also see that f of negative x equals x. If we plug in a negative number, it will, basically the square will undo the negative, so we'll get the same result as if we were to plug in a positive number. So this has even symmetry. And then it has both an x and a y intercept at the origin. This one has both increasing and decreasing behavior. So it's increasing on the interval from 0 to positive infinity. After 0, it starts increasing, and decreasing on the other side. So we can say decreasing on negative infinity to 0. And we have both a local and an absolute minimum. So remember, a local minimum means we can draw a little interval around a point and find a minimum. And this is also the lowest value in all of the domain of the function. You can't get a value lower than 0, unless if it was reflected or anything like that. So we would say a local minimum value of 0 when x equals 0. And same with the absolute. Let's say absolute min of 0, also when x equals 0. All right, next up is the cubic function, x cubed. Let's draw a graph. And first I'll say what we're doing. So f of x equals x cubed. So hopefully you recall the shape of this graph as well. Let's add some points. So I know he'll have the point 0, 0. 0 cubed is 0. 1 cubed is positive 1. And negative 1 cubed is negative 1. The odd powers preserve the negative. And if you recall, you get a nice curved shape. This will be 1, 1, 0, 0, and negative 1, negative 1. The domain, it goes forever in both directions from, this keeps going outwards to negative infinity, so from negative infinity to positive infinity. And same with the range. So unlike the square function, the cubic function covers all y values. And this was our example of a classic odd function. We can see if we plug in a negative, we get the negative version of our output. F of negative x equals negative f of x. We can also see the symmetry, imagine reflecting it across the y and then across the x. So we can say it's symmetric about the origin. So this is an odd function. We have both our intercepts at the origin again. And this function is increasing across its entire domain. If we go from left to right, it's always getting larger. We're always increasing as x increases. So I'll say increasing from negative infinity to positive infinity, never decreasing. And because it's continuously increasing, we don't have a local min or max or absolute min max, just like our identity function. So no local min max and no absolute. All right, next up is the square root function. So this is the square root of x. This one looks like, to me it always looks like a projectile that is not affected by gravity, so it keeps going off. So let's add some points. You can always create a table of values. If we plug in 0 for x, square root of 0 is 0. The square root of 1 is 1. The next one maybe I would do is 4, because the square root of 4 is 2. So maybe we would end up with this scaling maybe somewhere over here. And we could do 9, the square root of 9 is 3. So we should see that our function will increase So we get this kind of projectile shape. So we have this point 0, 0, and call this 1, 1. So this function has a restricted domain. Notice the function doesn't begin until 0 and then continues onward. Because we can't have anything, we can't plug in a negative value. Otherwise we get an imaginary result. So again, we're sticking to the real numbers here. So our domain is from 0, including 0 to infinity. And similarly for the range, the function starts at 0 and goes off to positive infinity. So no output would be negative of the square root function. It is neither even nor odd. Don't see any symmetry there. This also has an x and y intercept at the origin. It doesn't have a local minimum, but we do have an absolute minimum. So again, we can't call this a local minimum because we can't produce an open interval around it. It's at an edge point. So we can only include it as the absolute minimum of the function. So no local, min, max. And we do have an absolute min of 0 when x equals 0. So that's our starting point, and then it gets larger from there. We also have the cube root function. So what does this one look like? I feel like this one gets graphed less often. Well, what points would we have? The cube root of 0 is 0, so it definitely will have the origin point. The cube root of 1 is 1, so we'll definitely have a point there. The cube root of negative 1 is negative 1. You can have negatives in cube roots because the negative is preserved. Because we can say negative 1 cubed is negative 1. So the cube root of negative 1 is negative 1. And the shape, we still have this, kind of looks like x squared a bit going this way, but then it goes down and curves in a symmetrical way on the other side. So let's label our points. 0, 0, 1, 1, negative 1, negative 1. So this domain, unlike the square root function, we get all real numbers, negative infinity to positive infinity. Same with the range, because we can have negative inputs and outputs. It's an odd function. You can see that symmetry if we flip it across and then across again, or if we plug in f of negative x, that would be the cube root negative x. You can view that as the cube root of negative 1 times the cube root of x, or negative cube root of x, which is negative f of x. So f of negative x equals negative f of x. That's our pattern for an odd function. This has x and y intercepts at the origin. That's happening a lot for us for these parent functions or for the library of functions, but we'll see as things get shifted around, this will change depending on how the function has been modified. This function is increasing across its entire domain. Any point you have, the point to the right of it is a little bit higher. So it's increasing everywhere. So we can say increasing from negative infinity to positive infinity. Because it's always increasing, we don't have any local, so no local min-max. And no absolute min-max. So cube root of x. Next is the reciprocal function, so 1 over x. This one has some additional conditions. All right, so what does this one look like? Well, we know we can't plug in 0, otherwise we'll be dividing by 0. So we definitely have a vertical asymptote on the y-axis. This can also never be equal to 0. There's no value we can plug in that will make this equal to 0. So we also have a horizontal asymptote. And if you recall rules for horizontal asymptotes, you can see it from that perspective as well. 1 over 1 is positive 1. 1 over negative 1 is negative 1. So we definitely get 2 points there. Let me use my blue. And if you recall, you get nice curves in the first quadrant and in the third quadrant. So we get this discontinuous shape. So let me label these. 1 comma 1, negative 1, negative 1. So what do we have? What's our domain? Well, our domain is everything except for 0. It cannot be equal to, we can't plug in 0 for x. So let's state it. I'll keep using interval notation. We're good from negative infinity all the way up until 0, so we want to skip over 0 and then continue to positive infinity, not including 0. Just fixing my notes a little bit. Looks like I included my endpoints, but no, we would definitely not want to include 0 because we're skipping over 0. And then we can make a similar statement for the range. The graph exists all the way up until 0, then we're skipping over 0 and then continuing on. It can be equal to anything except for 0. So negative infinity to 0, union 0 to infinity. How about symmetry? This is an odd function. You can imagine flipping it and then flipping it again. You would get our graph. Or we can use the test f of negative x equals 1 over negative x, which is negative 1 over x, which is negative f of x. So there's our odd pattern. So we got an odd function. This time we have no x and y intercepts. Unless if this was shifted around. But as it is no intercepts, And this function is decreasing everywhere on its domain. If we start over here, we get decreasing behavior, or if we start over here, also decreasing behavior as we move from left to right. And then it's undefined at 0. So it's always decreasing. So decreasing on its domain. So from negative infinity to 0, and from 0 to positive infinity. Yeah, we can imagine plugging in larger and larger x values. Well, that will make us divide by larger and larger numbers. So we would expect it to get smaller. So that's our decreasing behavior. And then this one has no local min or max, and also no absolute min or max. Yeah, any point, even in these points, there's always a point to the right of it that is less. And coming from this way, there's always a point to the left of it that's a little bit higher because it's approaching 0 there. So it'll always get closer and closer and closer to 0. All right, next is the absolute value function. So recall what this does. If we input a negative number, it's going to turn it positive. So we can predict some kind of symmetry there. So absolute value function, if we plug in 0, we get 0. If we plug in positive 1, we get positive 1. If we plug in negative 1, we'll get positive 1 again, because it will turn it positive. And so you may recall absolute value function looks like a V shape. Sort of like a line where the left side has been reflected up into the positive realm. So we have this point 0, 0. This will be our point 1, comma 1. This will be negative 1, positive 1. Our domain will be all real numbers. We can plug in any value here. However, our range will have to start at 0 and go to infinity. It's going to turn everything positive, so we won't have any negative values as the output. This has even symmetry. And then we can say f of negative x would be absolute value of negative x, which will just be absolute value of x, which is f of x. So even symmetry. It has an x and y intercept at the origin. It goes from decreasing to increasing. So first it's decreasing from negative infinity to 0, and then increasing afterwards. So increasing from 0 to infinity. Here we have a local min of 0 when x equals 0. We have this little minimum. We can draw an open interval around it, and that will also be the absolute minimum. Of 0 when x equals 0. The last function that they give us is an interesting one. It's called the greatest integer function. This is also called the step function. So what does it do? It says it takes the greatest integer less than or equal to x. Meaning if we were to plug in something like 2.5, it would give us 2, the greatest integer less than or equal to x. So it basically rounds down any decimal. Even if we had like 2.999, it would still give us 2. It will round it down. So what will this look like? Well, let's draw our axes. So its outputs will only be integers. It won't produce anything in between our integers as outputs. So if we were to plug in 0, it would give us 0. Anything between 0 and 1, it's going to give us 0, except for at 1. So I would put an open circle there. At 1, it will give us positive 1. And then anything greater than positive 1 will just give us 1, all the way up until 2. Once it hits 2, it jumps up. So this is a highly discontinuous function. And this will continue. And we can imagine the same kind of behavior here going in the other direction. So this is where it gets that step name. It's the step function. It looks like a bunch of steps, and this continues in both directions. So what an interesting function. What is its domain? Well, we can plug any value into here. Its domain is all real numbers. Even though it's discontinuous, we can plug in any value. Its range, however, is restricted. Its range is only integers, so we can imagine every possible integer fast forwarding to like -3, -2, -1, 0, 1, 2, 3, and so on. So we can abbreviate this using this notation. It's like a z, the set of all integers. Similar, if we were to say r, the set of all real numbers, this is set notation for all of the integers. Now, what kind of symmetry does it have? If we were to flip it over the y-axis and then over the x-axis, notice it's going to change. We would end up with the opposite version where the right side would be filled in and then the left side would be open. So it doesn't hit that kind of symmetry. So I'll have to say neither even nor odd. Let's think about that. If we were to plug in f of -x, let's think of an example. Just doing this for partially for my own sake too. So let's take, if we plugged in positive 1.5, this would give us positive 1. So it will round down. If we were to plug in negative 1.5, well, the greatest integer less than that would be -2 and not -1. Yeah, so it sends it to the left. Yeah, if this was actually symmetric, then it would round it up to -1. All right, so that'll confirm it for me. Neither even nor odd. I had to pause and check for a second. Okay, how about intercepts? Well, we have x-intercepts on this entire little interval here. So we can say x-intercept for all x values in this little pocket from 0 to 1. So including 0 up until 1, but not including 1. Those are, you have an infinite number of x-intercepts there. And we have one y-intercept just at the origin at 0, 0. Now it's not increasing or decreasing, but it has a bunch of intervals of constant behavior that overall shift upwards as we go from left to right. So this can be a little tricky. How can we describe all of those intervals on which our function is constant? So how about this? We can say constant on this interval, and we have to be general. So let's use a k, starting at k, going to k plus 1, but not including it because we want to include the left endpoint and not include the right endpoint. And this will be for all k that's an integer. So for instance, when k is 2, so from 2 to 3. Yeah, from 2 to 3, not including 3, it's constant. Or from 1 to 2, not including 2, it's constant, and so on. So this actually captures all of those intervals. Interesting. All right. We won't really use this function that much, but it's cool to think about. It's cool to think about these properties. Okay, the second part of this section is on another type of function setup called piecewise functions. So let's take a look. So a piecewise function looks something like this, and they have one defined for us over here. They're saying f of x equals negative 2x if x is less than 0, but then it behaves like the square root of x if x is greater than 0. So it can switch behavior. If you've done some programming, think of it as like an if-then statement. If x is less than 0 and you're plugging it in, then you're going to process it with negative 2x. Else, if x is greater than or equal to 0, then you'll process it using the square root of x. So just to give a little programming metaphor. And these are our two conditions. So we can call this like condition A, and this one condition B. So let's go through a few example questions around this. The first one has us find a few values. The first is f of negative 4. So negative 4 is our x value. That's our input. So we just need to check to see which condition our input falls under. Is it less than 0 or greater than or equal to 0? Well, negative 4 is definitely less than 0. So then we should use that first definition. We can say f of negative 4 will plug into the negative 2x. So we'll say negative 2 times negative 4, or positive 8. Next is f of 0. Well, 0, we can say 0 is greater than or equal to 0, because we get the or equal to part here. So that means f of 0, we would use the square root function, since it meets that condition. So we'll take square root of 0, which is equal to 0. And then f of 4, positive 4 is also greater than or equal to 0. So that means f of 4 will use the square root. This will be equal to positive 2. So if they give you some values to evaluate, just look at your x value and then check which condition it falls under. And whichever one it does, you'll use that function to plug into. So it checks the input and then kind of sorts it into different categories. So how about the domain? Well, we can think about what the domain of each of these would be. The domain of negative 2x is negative infinity to positive infinity. Anything can be plugged into that. However, we really just want to think about when x is less than 0. And then the domain of the square root of x, we said earlier, is from 0 to infinity, including 0. So this function will be defined really for any input that we put in. It's defined from negative infinity all the way to positive infinity, since it's also defined here at 0 where it changes behavior. So there's no gaps. You can think of the intersection of these two domains would be all real numbers. Say domain of f of x is negative infinity to positive infinity. All right, C is asking for intercepts. Let's see, when x equals 0, when we plug in 0 for x, that'll give us our y-intercept. We did that earlier. We saw that f of 0 was equal to 0 up here. So that should give us our intercept point. And then also, we can think of when the function will be equal to 0. Well, we can see by looking at it, for both cases, that will be when x equals 0. So this is a case where our x and y-intercept are on the same point. So f of x is equal to 0 when x equals 0. And we kind of saw that here already. But maybe there were multiple places, so just to be sure. So we can say both our x and y-intercepts are at the origin, 0, 0. Now D asks us to graph this function. So let me just write it out again. We have f of x equals negative 2x when x is less than 0, and the square root of x when x is greater than or equal to 0. So it's going to change behavior at the origin at that 0 point. So what would this look like? Well, we can think about the graph of each of these separately. Negative 2x, that's a line with a y-intercept of 0 and a slope of negative 2. So we can imagine going down 2 and over 1, plotting another point. Oops. Or going up 2 and over 1. Get some line with a negative slope. But for this graph, so this would be specifically for y equals negative 2x, we're only interested where x is less than 0. So imagine just taking this left side. And then for the square root of x, we graphed that earlier. We know that it starts at the origin and then is like a projectile out from there. So you can imagine the point 1, 1. And for this one, we're looking at everything greater than or equal to 0. So just the right side. So the graph of our piecewise function, we're kind of cutting and pasting these two behaviors together. We just want to choose the left side of negative 2x and the right side of square root of x. So let's place it together on a single graph. So they both share the point at the origin. We said that's where our intercept was. On the left side, I know I'll have the point negative 1, positive 2. So this will be our line behavior coming from the left side. And then on the right side, it's going to look like the square root of x. So let's throw some labels in here. 0, 0. This would be the point 1, 1. And the point negative 1, positive 2. So you can build some pretty messy, like Frankenstein-looking functions out of this, but it's pretty cool. It means you can have a function that has multiple behaviors based off of some input conditions. So we're not bound by just one kind of function behavior. So that's pretty cool. All right, let's look at another example. This time we have 3 different conditions, but the process will be the same. So let's just check where our input falls under these 3 conditions, and we'll choose the associated output. So first is f of negative 2. And where's our function changing behavior? It looks like it will only begin at negative 3, and then at 1, it's going to change behavior to the second function, and then when it's greater than 1, it's going to change behavior. So really we're thinking around how is it, on what side of 1 is it? So negative 2 is less than 1, so it'll meet our first condition. So that means f of negative 2 should be negative 2 times negative 2 plus 1. So 4 plus 1 equal to 5. Next is asking for f of 1. Well, 1 is equal to 1. That's going to be that middle condition. So when the input is 1, when x equals 1, it's just giving this constant output as 2. So we'll just say this will be equal to 2. And then it's asking for f of 2. So 2 is greater than 1. It meets this third condition. So we'll plug into the third position. So f of 2 equals 2 squared for positive 4. So again, just check to see which condition your input falls into, and then use its associated function, whatever it appears next to. All right, part B, it's asking for domain of f. Well, these statements kind of give us our domain too. We can say that the domain on the first section is between negative 3 and positive 1, not including 1. Then we're going to join this with the domain of the second piece, which is just positive 1. So just this one piece, positive 1. And then we would join this with our domain of the third piece here, with x just being greater than 1, strictly greater than 1. So from 1 to infinity. So let's just combine these all together. In the first bit, we're stopping right before 1, but then we have 1 included here. And then the last bit goes from 1 to infinity. So really we could just say this function is defined all the way from negative 3, including negative 3, up to positive infinity. We'll say the domain of f is from negative 3 to positive infinity. So you can look at these because this is kind of telling you where your function is defined. All right, C is asking for intercepts. So we can say when x equals 0, that'll give us our y-intercept. Let's find f of 0. Which condition would that fall into? Well, it's less than 1 and greater than -3. So let's plug into the minus 2x plus 1. This would be minus 2 times 0 plus 1, or just positive 1. So that tells us we have a y-intercept at the point 0, 1. Now where's the function equal to 0? Where's f of x equal to 0? This will tell us where our x-intercept is. Well, without graphing it, how can we tell? Well, let's see for each individual condition. The first one is negative 2x plus 1. Set that equal to 0. I would subtract the 1 over, divide by negative 2, and I get positive 1/2. And that is in this little subdomain here. So that looks pretty good, but just to check the other two, for our second condition, 2 will never be equal to 0. So it's not going to exist here. And for the third condition, we can say x squared equals 0, so x equals 0. But it's only going to behave like this function when x is greater than 1. This is saying when x is 0. So we wouldn't need this part either. So our x-intercept will be at this value of positive 1/2. So I'll say x-intercept at the point 1/2, 0. It might be easier just to graph this and see what it would look like. So let's use a similar technique. Let me write out what the function is again, just so we can see it. So it has three conditions. The first one is negative 2x plus 1 when x is greater than -3, greater than or equal to -3, and less than 1. And then it behaves like 2 when x equals 1. So we'll see what that looks like. And then x squared when x is greater than 1. So what will this look like? Well, again, let's just think about each function separately. So first, let's say when y equals negative 2x plus 1. So this is a line with a y-intercept of positive 1. So I know it'll have a point up here. And it has a slope of negative 2. So I can imagine going down 2 over 1, following another point. So I could go to the left 1 and up 2. And continue on that way. So something like this. Next we have just y equal to 2. Well, that's just a horizontal line going through 2. And then our third condition was x squared. So y equals x squared. So that's our classic parabola centered at the origin. but we only want to steal certain sections of this. So our first one is from -3 to +1. You can imagine -3. If we plug in -3 here, that would be give an output of +7. So it's somewhere up here. Let's just label it. Let's just say, for the sake of our example, this is -3, 7. So we want to go from -3 up until +1. So really we're just stuck between this region. So we want to just steal this bit here. Our second condition is only when x equals +1. So we really are just getting a single point. We're going to steal this point. That point will exist on our graph, the point 1, 2. And then for x squared, this is when x is greater than 1. So it should start let me make sure that condition is correct. Yeah, when x is greater than 1. And strictly greater than 1, so we could imagine even just not taking, there's like a hole at that part, and then continuing. So strictly greater than 1. So that would be the part that we want to steal. So let's combine these all together into a single graph. So now this is when y equals f of x, our full function. So what are our points of interest? We know we should have this decreasing line. So I would have the point -3, 7, stick it all the way up here. It's a little bit out of scale. That's okay. So -3, -7, all the way up until what point? It looks like until x equals 1. So that's that point, +1, -1 on that line. And not including 1. So we should have an open circle down here. And it looks like it's hitting that, let's see, we said we had an x-intercept at 1/2, 0, so almost looks like that. I think my scaling kind of threw this off. And then pretty much looks like it's going through 0, 1, so we're pretty close. So that looks pretty good. Now, at 1, we have it defined as +2, so we have that single point that we're like stealing. So we can imagine a single point here, and then our parabola begins at the point 1, 1, but with an open circle, and then continuing on from there. And on to infinity. So kind of a strange looking function. But it's a combination of our 3 different behaviors. So I'd recommend graphing each one separately. It can just be a sketch and think about which region you want to steal from to combine together into your final function. It can be hard to try to put them all together at the same time. So it was asking for the range. I think that was part of D. It said use the graph to find the range. Well, it looks like it's starting down here at -1 and going upward from there. And even though there's some holes in the graph, it's always going to be defined at that, like it's still defined at this point. There's nowhere where we have to skip an output. We're just sort of shifting around. So we can say the range, we'll just stick it up here, is from -1 to +infinity. And notice it is still defined everywhere, even though we have these holes. At this point where it's shifting behavior, the function is still defined, even though it jumps around. So definitely not continuous, but it is defined everywhere. starting at -3. So anything beyond that we would not include. All right, let's finish off by looking at an example, some kind of application. So this is around the cost of electricity. Electricity plans can be complicated. A lot of times there's very complex pricing plans for utilities and things like that. So let's see. It says in the spring of 2018, Duke Energy Progress supplied electricity to residencies in South Carolina for a monthly customer charge of $8.29 plus 8.6035 cents per kilowatt hour for the first 1,000 kilowatt hours supplied. So think of that as our first condition. And then it changes behavior, and then it's just 9.1446 cents per kilowatt hour for all usage over 1,000 kilowatt hours. So you can already see there's like two conditions, and then the price behavior will change. So first it has us find a couple values. It asks us, what is the charge for using 500 kilowatt hours in a month? Well, it definitely falls within the first 1,000, so it's only going to hit that first condition. We can say 500 is less than 1,000 to continue this kind of method. So our charge should be equal to, how are they describing it? $8.29 plus, and let's convert this to dollars, so I'll move the decimal place 2 places over, so 0.086035 per kilowatt hour, and we used 500 kilowatt hours, so times 500. If you plug this in, work it out, you should get $51.31. So we only plug into the first condition then. Part B, what's the charge for using 1,500 kilowatt hours per month? So this is where it gets a little tricky. So 1,500 is definitely greater than 1,000. But we wouldn't just plug it into the second rate because we still want the first 1,000 hours to be charged under the first rate. So we need to kind of think of it in two pieces. We can say for the first 1,000 kilowatt hours, we're going to follow the first pricing method. So that was $8.29 plus 0.086035 for the first 1,000 hours. And then there's the 500 hours remaining. That's what's above 1,000. So we can say for the remaining kilowatt hours, that above 1,000, it just charges 9.1446 cents. So let's move that into dollars. So 0.091446 times the remaining hours. And we could put 500, but I want to express it as 1,000, or I'm sorry, 1,500, the total amount. So this is where the total amount will show up, minus 1,000. So minus the amount that we've already used up. And I'm doing it this way because this will help us build the actual equation. So our charge should be our first bit, 8.29 plus 0.086035 for the first 1,000 hours plus 0.091446 for the remaining 500. Well, we could express that as our total amount, 1,500 minus 1,000. So if you plug this in, you should get $140.05. So how can we describe this using a piecewise function? It's obviously changing behavior, so we want to be able to describe how it will work out, how it will be calculated. So it's asking us to build a function called c of x that will build the charge. So let's think more generally. Instead of 1500, let's just say let x equal the number of kilowatt hours used. We know for the first 1000, meaning when x is greater than or equal to 0 and less than or equal to 1000. Notice I'm starting to build my conditions here. When x is in that range, then our output should follow that first formula. That was $8.29 plus the 0.086035 times however much was used. So we can just say times x. And we're saying this is when we are less than or equal to 1,000. And obviously more than 0. We wouldn't imagine negative kilowatt hours. Although I guess if you had solar panels, there's some plans that will pay you back some money if you contribute to the grid. But I think we won't consider that here. So how about for over 1,000? So for over 1,000 kilowatt hours, meaning this is when x is greater than 1,000. Well, again, we wouldn't just say that second formula because we need to assume that we've already paid out the first $1,000 under that first rate. So we can frame it like this. It will be the first rate for the first 1,000, so 8.29 plus 0.086035. My pen's kind of acting weird here. Times 1,000, because we know the first 1,000 will be under that rate. And then plus our second rate, which was 0.091446, for whatever the remaining amount is. So here's where it's useful to say x minus 1,000. Whatever our x value is, we would subtract 1,000 since that 1,000 has been paid under this rate, and then the remaining, this gives you the remaining amount that will be charged under our second rate. So let's just clean this up a little bit. Oops. So this will be 8.29 plus, this will just move our decimal point. So this will be 86.035 plus, and let's distribute the 0.091446, so 0.091446x minus, and then times 1,000, so that will move that decimal place, 91.446. And then let's combine some like terms. So we have 8.29 plus 86.035 minus 91.446. We still have this 0.091446x. And then combining all those like terms, we should get plus 2.897. So just simplifying things. So let's build our function. We can call it c of x. It has two behaviors. Our first behavior we have here. So it will look like let's see. Yeah, let's put it in like slope-intercept form. 0.086035x plus 8.29. So just flipping those around. And we're saying that this is when x is greater than or equal to 0 and less than or equal to 1,000. And if it's more than 1,000, then we went through this process where we took care of the first 1,000 under the first rate and then took the remaining amount times the second rate. And we cleaned it up into this nice statement at the end here. So 0.091446 x plus 2.897. And this is when x is greater than 1000. And that will be our function. So we've created a piecewise function. Maybe you would program this into a spreadsheet or something to input the customer's kilowatt hour usage, and then it will produce their bill at the end. So it gets a little tricky for the second statement. We have to include running the first however amount through, in this case it was 1000 kilowatt hours, through that first statement, and then picking up where we left off with the remaining amount. That's what we did here. It's just an example of building one of these through some kind of word problem. All right, that was section 2.4. So we looked at all of our library of functions, also known as the parent functions. And then we also looked at piecewise functions and how we can determine their properties, graph them, and then build one out of some situation. So that'll be it for this video, and I'll see you next time.